Yes.
Okay, perfect. So I'm gonna, for the next 10 minutes, I'll talk about PlanetVac, which is a sample acquisition delivery.
Can you put the slides in slideshow mode?
Is this better?
Thank you.
Yeah, thanks. The PlanetVac actually will be flying on Eclipse and on a PI, but we also have co-eyes from NASA Kennedy, Mueller, Jason Schuler, and Ivan Townsend. A bit of a background. Traditional way of delivering samples is using scoops and robotic arms, and this is what previous speakers spoke about. They relatively versatile, and that's why they've been used on so many missions. But they have also several drawbacks. Massive one of them, you require a massive arm, but also mass of avionics, which could be a couple of kgs for its, $5 arm. Power, you don't need just the power to actuate robotic arm, but also power to warm up the actuators if you're sitting away from the sun or if it's early in the morning. In fact, on the Mars missions, a lot of power was essentially spent warming up actuators. The cost is not just the hardware, but also software, unless you do sort of human in the loop, so it's teleoperated system. We had, on Mars, we had obviously a lot of problems, positioning arm in the right locations because of inaccuracies and things like that. So if you control it, for one, ideally would be human in the loop. So essentially you need to pay this person to sit in the control. In delivering of samples, you actually rely on gravity. So sticky, or you have, or it's very cohesive, you may have problems. And this is what also we found on Mars with a sticky material. So we actually Honeybee built a scoop who had a percussive system which helped with delivering of samples. Then you're talking about acquisition time and delivery and kinematics. Whenever you design a scoop and you design instruments where the sample has to be delivered, you have to put the arm in the right orientation so it can reach the ball. Somebody has an open mic and making coffee or dinner. A solution to all of this is PlanetVac. It's essentially very similar to our usual vacuum cleaner, but works in reverse. There are three steps in a PlanetVac system. The first one is lofting material, and to do this, we use compressed air to blow up and stir up material and trap it inside the tube. Then we have a transfer line, which means we don't really care where the end instrument or sample return container is, because transfer line can be flexible. And when it comes to the capture of material, there is plethora of ways we can capture it depending on the type of instrument. In fact, the bottom deflector plate is what we're flying on a Dragonfly mission to Titan, and sort of a catch can type system is what we're flying on a MMX mission to Phobos. The nice thing about the pneumatics is it's essentially based on a cold gas propulsion. So tanks, valves, and all of this stuff is used in the cold gas propulsion, so it's TRL9. The only difference is what we're using, how we're lofting the samples, that can range from TRL1 to 7, and how we capture it. And when it comes to benefits, very simple operation. You just have to open a valve and the sample appears in where it's supposed to be. Very short sampling time, literally seconds or less. There is no ground inner loop. It's gravity agnostic, so it can work with a sticky material. And the sample delivery location can be anywhere on the lander. So it's in a position, the best location, and the sample acquisition is put in the best location for sample acquisition. This video essentially shows one of the sample delivery methods for GCMS caps, gas chromatograph mass spectrometer. As you can see, the material is flying through the tube. Deflector cap pushes the sample, bounces the sample into the cup, and then this cup is removed from a capture system and positioned into the GCMS instrument. This is a PlanetVac with a drill in case material is very competent. On the bottom left-hand side, what you see is a PlanetVac sort of a sampling head with a drill essentially piercing right through. The drill brings the cuttings, so IC cuttings to the surface, and then pulse of gas moves the sample into the carousel. We actually have done on the right-hand side many tests in a vacuum chamber in different simulants, and the cutout that you see on the right-hand side, the picture shows material transfer and completely fills the cup. So this cup can be moved into GCMS, could be moved into LDMS, it could go into XRF, XRD, Raman spectrometer, microscopic imager, and many other instruments. Or it could be also sample return. For clips, we're gonna be flying a PlanetVac, which is gonna be mounted on a footpad or close to the ground. The sample is gonna be moved into what we call triage station that's sitting on a landed body. The pictures at the bottom show essentially what we expect to be delivered. So you have rocklets and with some regolith. And then we're gonna send a puff of gas to blow away fines and leave rockets behind. And this is technology demonstration to show that we can actually acquire small rocks for geochronology mission. For example, Barbara's Carly instrument, or it could be also rocks for sample return mission, like a New Frontiers sample return mission from a South Pole Aitken Basin. The system is also flying Martian moon exploration mission to return samples from Phobos, and since Phobos has some probably Martian sample, it could be the very first Mars sample return mission. The sampling system sits on along a leg of a spacecraft with the sampling head very close to the footpad, and all the plumbing at the back end. We've done, this slide is old, but we've done hundreds of tests with different simulants. What you see is a sampling head capturing a sample into the sampling canister on the right-hand side. And this movie actually, if you don't catch everything, it's on YouTube. Our goal is to capture sample from 10 centimeter distance. So the PlanetVac would not be in contact with the regolith, and deliver sample to a sample canister at the back end of this tube. This is slowed down to a quarter of the speed. We injecting high pressure gas that blows regolith in all the directions. Some of the regolith flows into the sampling head where another jets pointed towards the sample container essentially push the sample in. So with 10 centimeter standard distance, we can capture a couple of, we can capture like 1 gram or 2 grams of sample at least. Again, these two things are flying to the moon, to Mare Crisium, and that's what we're building right now. So I'll be happy to answer some questions.
Thank you, Kris. Are there any questions for Kris? Okay, well, unfortunately, the next speaker had to cancel, so we unexpectedly we just received word that Dr. Cohen couldn't make it today. So, if there are any other questions for previous speakers, who, if you had questions who you didn't get to ask, now would be a good time for it. Especially for the first speaker, who we didn't sort of have any questions. If there are any questions for the first speaker, that would also be a good time to ask those as well.
Actually, I have a question for the sampler team. What's the force can you apply during excavation? And when the arm is stretched out? So there is actually a question from Bob. How much the soil? Can you actually hear me?
Yep,
Yeah.
I can hear you.
Yeah. So there's a question: how much we're losing by blowing stuff out? It's a good question. It's a function of how far we from a surface. Our requirement for MMX is essentially any sample. There is no mass or volume requirement. So we're capturing actually we're capturing a couple of grams, but when we far away from from a surface, we definitely lose a lot by blowing in all directions. So this is sort of one of the R squared kind of stuff. Further away you out from a surface, more you're gonna be losing. Closer you are, you're gonna capture everything. When we in fact right on the surface, we fill out the cup. PlanetVac was flown on a Marston lander last year as part of the Space Tech Red Eye, and we captured something like 300 grams of a stimulant within like few seconds. So if we're touching the surface, we're capturing hundreds of grams essentially. And in the third quarter, we're gonna be flying again to test different generation of the PlanetVac.
Thanks, Chris. Is there any other questions for Chris or any other previous speakers? And the answer to Tim's question here online is that Barbara was unable to produce slides, and so we're unfortunately that's not an option.
Yeah, I have a question for Chris. This is Rick Arable at University of Maryland. Maybe I joined a little bit late and you guys are incredibly on time. Maybe you said this, but do you have like a particle size distribution? And I know that's going to be sensitive to what the regolith is, but do you guys have like a fraction? Have you evaluated if you obviously have a bias towards collecting finer particles than larger particles as a function of distance, for example?
Yeah, we do. There is a bias. The only way around it is essentially increase gas pressures to capture everything. To essentially gas is used like a broom that scoops out the material. So if we want to capture everything, we just have to increase the pressure of the gas. Then in most of our tests, we wanted to make sure we capture rocklets, centimeter to centimeter rocklets.
Mm-hmm.
We have also developed new simulant called based on the accrete. We crushed it and blended to have a size distribution that of Apollo, I believe 14. So with some fraction of rocklets to show that actually we can capture rocklets. And, the pictures that you saw in my presentation, I can share again and show you this picture.
But I mean, what you're telling us is you can fine tune the gas pressure and I assume also maybe the proximity to the surface to allow you access to larger grains if that were an objective of the mission.
Correct. And so like you see here, you know, rockets and regolith and rockets that behind. Yeah.
All right, thank you.
Okay, any other questions? There was a question previously from John Gruner, who had to step out of the office here. Will Lister be tested in icy regolith for possible use on a polar mission?
I'm not sure if CH is online, but I can jump in. So Lister is designed for granular material. It's not designed for competent material, at least for now. It cannot penetrate icy soil. To do that, we actually have a hammer drill called Trident. It's baseline for Viper rover. It could also be used on a lander. A drill on a lander has been deployed before by Luna 16, 20, and 24. These were sample return missions from the Soviet Union. So that kind of you know, arrangement or architecture is possible. We are developing augmented Lister for Europa, sort of Europa lander. And it has a small drill bit and a motor at the bottom. So future Lister type architecture could potentially cut through icy soil. And Laura is asking about how hard of a vacuum we tested PlanetVac in. We tested in a Martian vacuum, so a couple of top pressure. The thing about pneumatic systems is the efficiency gets better as you drop, you know, from partial vacuum like Mars vacuum into hard vacuum. Gas in vacuum is like explosive. So at 1 atmosphere, you know, you really need a real explosive to generate a lot of you know, a lot of air or gas. Whereas in vacuum, the gas as it comes out from a canister, it essentially hits choking velocity right away. In fact, we flew we had a test on a reduced gravity flight at 1.6G and Martian vacuum, and our sampling efficiency was 1 to 6,000. So 1 gram of gas at 6 psi absolute lofted 6,000 grams of soil. With listed type systems, we see efficiencies of 1 to 100, 1 to 500. So 1 gram can lift 100 to 500 grams of soil. So it's super efficient. And Sam, hey Sam, is asking another question for whether we can get specific size distribution for. Yes, that's possible. We can put inline sort of filters and we've done it for some of applications. For example, CAMN, it's X-ray diffraction instrument on the Curiosity, requires particles sub 150 microns to get you know, enough crystal planes for X-ray diffraction. So we looked at, for example, sieving it to sub 150 micron or even less. And the same, as you know, the fine particles, the charging could be significant and they're gonna, you know, stick to everything. So if you were to try to sieve it traditionally using screens, that would be a problem. But the gas is very powerful. The gas essentially overwhelms gravitational forces and static electricity as well. So that's the only way to essentially do some real sieving.
All right. Any other questions for Kris or previous speakers? Apparently Kris's talk stirred up a lot of positive questions here, which is good to see.